Alright, now we will start answering the questions about chapter 9, first section 1. The difference between the insulator and semiconductor. Insulator and semiconductor is the number of electrons in the valence band, the temperature of the material, the energy gap value, explain the motion of the electrons on the basis of Bohr's theory. So C is the correct answer. Because in insulator, this energy gap value is about 5 electron volt. It's very huge, so electrons in the valence band cannot transit to the conduction band. But for semiconductor, it is 1 electron volt, so when the semiconductors are heated, electrons can excite from valence band to conduction band, so this makes the difference. Question number 2. Which of the following is not able to move and conduct electricity? So an electron in innermost shell of the copper atom. Innermost electrons are unable to be removed from the atom. B, a valence electron in the copper atom in the wire. Valence electrons can be easily removed from an atom, copper atom, because when we apply potential energy, so electric field can give enough energy for valence electrons, so this is possible. Not able question, normally we got the answer is the correct answer. C, an excited electron in the conduction band in selenium semiconductor. Excited atom in conduction band in selenium semiconductor, when they are excited, when the electrons in the conduction band are excited, they jump valence band to conduction band and conductivity starts, so this is correct for conductivity. An electron in the conduction band of a semiconductor, for semiconductors, the electrons must be in conduction band to provide conductivity, but for conductors, for copper atom, for example, they can be in valence band. So A is the not able to move an electron in the innermost shell of the copper atom, so they cannot conduct electricity because they cannot jump from this innermost energy level to the conduction band. Question number 3. The longest path wavelength of a photon that will promote an electron in silicon from valence band to conduction band at the temperature of 300 Kelvin is approximately 1.1 times 10 to the power of -6 meter. This is the wavelength of that photon which can excite an electron from valence band to conduction band. What is the approximate value of the energy gap of silicon? Of course, energy of the photon must be equal to energy gap value, because if a photon is able to give enough energy to make the electron jumping, so energy of the photon must be equal to the energy gap value for the silicon. So let's calculate the energy of this photon. Energy of the photon in chapter 8 we learned that can be calculated h times f, but f is not given in here. The wavelength is given, so we should write this equation in alternative form, which is hc divided by lambda. So h is given, c is given, lambda is given. So let's calculate energy gap value. So E is equal to h 6.63 times 10 to the power of -34. C is 3 times 10 to the power of 8 divided by lambda. Lambda is 1.1 times 10 to the power of -6 meters. So let's calculate this energy gap value. 6.63 times 10 to the power of -34 times 3 times 10 to the power of 8 divided by bracket 1.1 times 10 to the power of -6, close the bracket. Answer is 1.8 times 10 to the power of -19. 1.8 times 10 to the power of -19 joule. So answer is C. Now let's continue with the problems, mystery questions about section 2, which is about the types of semiconductors. Question number 1, which of the following are equivalent to conventional current from left to right? So electric current from left to right. Electrons traveling from left to right. No, if electrons are traveling from left to right, electric current must be opposite from right to left, so this is not the correct answer. Holes traveling from left to right, holes are assumed to be positively charged particle and they are moving in the same direction of the electric current. So if the hole's direction is from left to right, it is the same as the electric current direction, so this is correct answer. Holes traveling from right to left, they are moving from right to left, so electric current means it's from right to left. So this is not the correct answer. Electric current must be according to question, left to right. In here is the B correct answer. The motion of holes in a semiconductor is always in the direction opposite the motion of electrons. Correct. Holes are assumed to be a positively charged particle. Electrons are assumed to be negatively charged particle. They are negative. So motion of the holes are in the opposite direction of motion of electrons. This is correct answer. Let's check B and the rest. Motion of the holes is always in the same direction as the motion of electron. Not correct. Varies with the type of not correct. Reverse it again, not correct. So A is the correct answer. In p-type semiconductor, the negative ions are majority of charge carriers. In p-type semiconductors, holes are the charge carriers. So holes are majority charge carriers. This is correct answer. Let's check electrons. As we know, not. Number of electrons and holes are equal. In p-type semiconductor, maybe you can say number of positive charge and negative charge are equal, but number of holes and electrons are equal. No, this is not correct answer. Question number 4. Which is likely to contain the most holes? A semiconductor doped with 3 valence electrons, because intrinsic semiconductors, just like germanium and silicon, they have 4 outermost electrons. When we add it into this structure for an atom, which is called impurity, with 3 valence electrons, so all 3 makes bonding, and then location of the 4th one stays empty. So this empty place is called hole. And question number 5, a semiconductor containing acceptors is known as acceptors. Intrinsic semiconductor, no, intrinsic is pure, so you shouldn't add any foreign atoms into structure for intrinsic. This is not correct. P-N type, we don't have such a definition of P-N type. N-type semiconductors, have additional electrons. So these electrons are donated from the impurity structure. So this atom is called donor atom, not acceptor. P-type semiconductor, correct, because P-type semiconductors have holes, empty space, so they accept electrons from the solid. So that's why this is P-type semiconductor is the answer in here. Now we will continue with p-n junction diodes. The p-n junction conducts current of the same intensity in both directions. Not diodes are the devices which conduct, or p-n junction conducts electricity only in one direction, not both directions. In reverse bias, p-n junction does not conduct electricity. In forward bias, it conducts electricity. Question number 2. One of the following is used as a rectifier. Rectifier is another name of the diodes, in fact. Resistor, no. Superconductor, no. Voltmeter, no. Diodes, or p-n junction diodes. This symbol is used for which of the following? So it is for diode. Of course, this is the symbol of the diode, and the direction of the arrow shows direction of the electric current, which is called forward biased. Question number 4. In the circuit at which diode is used as a rectifier for an AC current, which of the following are used as the filter? So filters are capacitors. Capacitors are filters which changes this pulsating direct current to much better direct current by filling this empty space. That's why they are called filters. Question number 5. A diode is connected to a source of alternating current. So the current is in the source fluctuates between -1 and +1 milliampere. What will be the range of the rectified circuit? So if the electric current, AC current is changing between two maximum values, one of them is positive maximum, +1 milliampere, the other one is negative maximum, -1 milliampere. But rectifying circuit, when we use diode, the diode crops one part, it can crop negative part or positive part depending on how you connect the diode, but this time output current after the passing from the diode will change between 0 and +1 or 0 and -1. So in the choice it's given 0 milliampere and +1. So answer also could be given 0 milliampere and -1, but it's not given in the question. That's why C is the correct answer in here. Which of the following is used as a AC rectifier to convert alternating current to one direction current? So of course we are using diode for this. We just explained this. So diodes are converting AC to one directional current. With just one diode is used as a rectifier of an AC current, shape of the output current will be diode will be like this. This is the AC current. C is AC current. Diode is cropping only one half of this AC. It can crop here or it can crop above. So according to choices, D is correct, which means negative part is cropped, only positive part remains. So it lets on the positive half of the ones of the cycle. This is all about the PN junctions. Now let's continue with the questions about transistors. PNP transistors differ from NPN. So remember, in PNP transistors, N type is in the middle, but NPN, P type is in the middle. So only difference is the way the semiconductor layers are arranged. So if the N type is sandwiched between two P types, so it is the PNP. If P type is sandwiched between two N type, it is the NPN. So this is the correct answer. For junction transistors to be used as a signal amplifier, so both junction, emitter base and base collector must be forward biased. This is not correct. Emitter base junction will be forward biased. Emitter base junction will be forward biased, but base collector must be reverse biased. So this is the correct answer. Which of the following equation represents the relation between the collector current and base current? So remember, collector and base current are directly proportional. As the base current changes, collector current proportionally changes. So the proportionality constant between them is known as beta. This beta is the current gain. So equation is IC is equal to beta times IB. So B is the correct answer in here. The symbol represents, this is the symbol about the PNP transistors, which is studied in the book. So PNP transistors. NPN transistors, in NPN transistors, the direction of the arrow becomes opposite. So if the question was about NPN, so in this case you should draw the arrow in this direction, so it's going to be NPN, but this symbol belongs to PNP transistor. The value for the current gain for an amplifying transistor is likely to be, current gain is always greater than BEM because IC is equal to beta times IB, base current, so beta is equal to IC divided by IB. We know that collector current is always greater than base current, so if because collector current is greater than base current, so what must be the current gain? Greater than 1, so more than 1. If the current in the base terminal is decreased, output current in the collector proportionally decreases. There is a proportionality between them. So also decreases, even proportionally decreases. The junction transistor contains how many PN junctions? There are 2 PN junctions. One of them is the emitter base, the other one is collector base. There are 2 junctions. This is all about the transistors. Now about superconductors. Let's answer the questions about superconductors. Let's answer them. Superconductivity starting when temperature of the material is rising. No, opposite. We should drop the temperature. Increasing the resistance of the material. No, decreasing. Temperature of the material is come close to 0 Kelvin. This is correct. So when you cool down the temperature, the material to a very low temperature, so superconductivity is observed. According to BCS theory, when the 2 electrons of the Cooper pairs travel through the superconductor A, there is a direct attraction between them. It's impossible. Then 2 electrons can never attract each other. They are negatively charged, negative repulse negative. There is no direct attraction between them and their linear momentum is conserved. No direct attraction between them, correct. Linear total momentum is conserved, also correct. Let's check to see. Their linear total momentum is not conserved. No, it's conserved. There is a direct interaction. There is no direct interaction, the indirect interaction between them and their linear momentum is conserved. So B is the correct answer. When the temperature of tin is reduced to a certain temperature that is well above the absolute zero, tin becomes a superconductor. Suddenly, it becomes a superconductor. It is tin. In which of the following a superconductor could not be used? So magnetic levitation is one of the way we use superconductors. Transmission of the electrical energy without loss, it's a good way because superconductors have no resistor, they don't lose energy. In saving electrical energy, correct. As a heating element, not correct, because to use the device as solid as a heating element, it must have a resistance. Otherwise, there will be no energy lost. Remember, power lost is equal to, we learned in chapter 6, I squared times there must be a resistance to produce a heat. Question number 5. The resistance of the blah blah material becomes zero at the temperature near the absolute zero. Superconductor, of course. This definition is superconductor. Barden-Cooper-Schrieffer BCS theory is the first microscopic theory developed for superconductors. Which of these substances becomes a superconductor when it's cooled to a certain temperature near zero? So silver never becomes superconductor. That's why the answer with the silver must be removed. Tin is correct answer. Now none of the silver and tin, no, tin can be superconductor at some temperature above absolute zero.